Swayam Prabha. Digital India. Educated India.
Welcome to lecture 24 of time series modeling and forecasting. In the last lecture, we have discussed how can you develop best linear unbiased predictor for the future values of time series model. Provided the time series is stationary and invertible, we observed that the best linear unbiased predictor is given by expectation of y t plus h given the information up to time t, say we denoted by f t, then expectation of y t plus h given f t. So, this gives you the best linear unbiased predictor for y t plus h. Now, we are going to apply that result for obtaining best linear unbiased predictors for different time series models like autoregressive model, moving average model and ARMA model. So, first we consider the stationary AR1 model. So, your process is y t equal to delta plus phi 1 y t minus 1 plus u t, and we assume that the process is stationary. So, mod of phi 1 is less than 1, and then f t is the information set up to time t, and just for convenience we denote expectation of y t plus h given f t by expectation given t y t plus h. So, these two are the same. Then h step ahead forecast is the conditional mean of y t plus h given y 1 y 2 y t. This y 1 y 2 y t constitute the information set up to time t. So, we apply the result which we have proved in the last lecture, and then we observe that the best linear unbiased predictor is the conditional mean of y t plus h given this information set. Now, for AR1 process, expectation of y t plus h given y 1 y 2 y t, say expectation t y t plus h is equal to expectation t delta plus phi 1 y t plus h minus 1 plus u t plus h. So, actually you have written y t plus h is equal to delta plus phi 1 y t plus h minus 1 plus u t plus h, and then you have taken the expectation, the conditional expectation given the information up to time t. Then the expectation of delta is obviously delta. Expectation of phi 1 into y t plus h minus 1 is equal to phi 1 into expectation t y t plus h minus 1, and expectation of this last term is equal to 0, means expectation of u t plus h given the observations y 1 y 2 y t, or given the information up to time t, this is equal to 0. So, y hat t h is equal to delta plus phi 1 y hat t h minus 1, because this part gives you the h minus 1 step ahead forecast value. So, you get this kind of recursive relationship between the h step ahead forecast and h minus 1 step ahead forecast of the AR1 process. Then we solve this equation recursively. For h equal to 1, we obtain. Now, we solve the equation 13 recursively, and we first take h equal to 1. So, y hat t 1 is equal to delta plus phi 1 y hat t naught. So, this is your equation 13, and you have taken h equal to 1 here. And then this is equal to delta plus phi 1 y hat t naught means 0 step ahead forecast. So, obviously, 0 step ahead forecast means y t itself. Then for h equal to 2, you have y hat t 2 equal to delta plus phi 1 y hat t 1. Then we substitute the value of y hat t 1 from here. So, you get delta plus delta phi 1 plus phi 1 square y t. In general, after moving h step, you obtain y hat t h equal to delta into 1 plus phi 1 plus phi 1 square, so on phi 1 to the power h minus 1 plus phi 1 to the power h y t. So, this is the h step ahead forecast. Then this series is a geometric series, and sum of this series is 1 minus phi 1 to the power h upon 1 minus phi 1. So, ultimately you obtain y hat t h equal to delta 1 minus phi 1 to the power h upon 1 minus phi 1 plus phi 1 to the power h y t. And then we write it as, we take delta upon 1 minus phi 1 here, then you have minus phi 1 to the power h, we take common between these two terms. So, you take phi 1 to the power h common here, inside you get y t minus delta upon 1 minus phi 1. Now, remember, for AR1 process, mean of the process is delta upon 1 minus phi 1. So, suppose mean is mu, then mu is equal to delta upon 1 minus phi 1. So, here also you get mu. So, you get mu plus phi 1 to the power h y t minus mu. So, you observe that as h increases, this value phi 1 to the power h declines exponentially. So, mu equal to delta upon 1 minus phi 1 is the mean of the process, and as h tends to infinity, phi hat t h is equal to mu plus phi 1 to the power h y t minus mu, and this tends to mu because mod of phi 1 is less than 1. So, phi 1 to the power h tends to 0 as h tends to infinity. So, ultimately phi hat t h converges to the mean of the process mu, and this convergence is monotonic if phi 1 is greater than 0, and this convergence is oscillating if phi 1 is less than 0. But in both the cases, y hat t h converges to the mean of the process mu. So, what does it mean? It's if your forecast value of forecast horizon is very large, h is very large, then your forecast value is the mean of the process. Again, you can write the AR1 process as y t equal to delta plus u t plus phi 1 u t minus 1 plus phi 1 square u t minus 2 plus so on. So, you can write it as a moving average process of infinite order. Then forecast error and its variance are, say forecast error is f t h equal to u t plus h plus phi 1 u t plus h minus 1 plus so on plus phi 1 square u t plus h minus 2 plus so on plus phi 1 to the power h minus 1 u t plus 1. Remember, your forecast value is this. And then the forecast error f t h is equal to y t plus h minus y hat t h, and then you can easily verify this expression for f t h. And variance of f t h is equal to sigma square u 1 plus phi 1 square plus phi 1 to the power 4 so on, and the last term is phi 1 to the power 2 h minus 2. You can easily obtain the variance of f t h just like the variance of moving average process. And then again this is a geometric series, and the sum of this geometric series is you have 1 minus phi 1 to the power 2 h upon 1 minus phi 1 square, because common ratio here is phi 1 square. And of course, sigma square u is also here. Now, as h increases, this term decreases. Phi 1 to the power 2 h decreases. Actually, it tends to 0 as h tends to infinity. So, variance of this forecast error increases as h increases, and as h tends to infinity, this variance tends to sigma square u upon 1 minus phi 1 square, which is actually the variance of original variance of y t. And this is logical also. If you keep on increasing the horizon of the forecast h, the value of h, then the variance also keeps on increasing. Variance of forecast error also keeps on increasing. Now, we consider the forecasting for a stationary ARP process. One more thing you notice here is that for obtaining the forecast value, we have used the auto-recursive representation of the process, whereas for obtaining the forecast error and its variance, we have used the moving average representation of the process. So, we come to the stationary ARP process. Your process is this: y t equal to delta plus phi 1 y t minus 1 plus 1 plus phi p y t minus p plus u t. Then Again we denote expectation of y t plus h given the information up to time t f t by expectation subscripted by t y t plus h. Then expectation t y t plus h is equal to delta is a constant, then phi 1 expectation t y t, you just replace this t by t plus h. So, you have y t plus h minus 1 here plus 1 plus phi p expectation t y t plus h minus p. And of course, expectation of u t plus h given f t is equal to 0. Then expectation t y t plus s is equal to y hat t s if s is greater than 0, and for s less than or equal to 0, this expectation is equal to y t plus s itself. For example, if you suppose you take s equal to minus 1, you take s equal to minus 1, then expectation t y t minus 1 given t or given the information up to time t means you have the observations y 1, these observations are given. So, obviously, y t minus 1 is given, and given y t minus 1, this expectation is equal to y t minus 1. So, for s less than or equal to 0, this expectation is y t plus s itself. Now, we solve these equations recursively. For h equal to 1, you have y hat t 1 equal to delta plus phi 1 h equal to 1. So, here you get expectation t y t, which is equal to y t itself, plus so on plus phi p. Here you obtain expectation t y t plus you have taken h equal to 1. So, y t plus 1 minus p, this is also negative. So, expectation is y t plus 1 minus p itself. Then for h equal to 2, y hat t 2 is equal to delta plus phi 1. Now, h is equal to 2. So, you get t plus 2 minus 1 means t plus 1 here, and expectation t plus 1 is equal to y hat t 1. So, you write y hat t 1 here plus phi 2. Next term is for h equal to 2, the next term is y t, and expectation t y t is equal to y t itself plus 1 plus phi p y t plus 2 minus p, and so on. So, this is how you can obtain the different forecast values, means the forecast values for 1 step ahead, for 2 step ahead value, and so on recursively. Say for instance, y hat t 3 will be equal to delta plus phi 1 y hat t 2 plus phi 2 y hat t 1 plus phi 3 y t plus so on plus phi p y t plus 3 minus p. So, this is how you can obtain different forecasted values recursively for ARP process. Now, we come to invertible MA process. So, you have this MA process y t equal to mu plus u t minus theta u t minus 1. Again, for invertibility, we assume that mod of theta is less than 1. So, that the process is invertible. Then we observe that expectation t u t plus 1 is equal to expectation of u t plus 1, and this is 0, because given t means u 1, u 2, so on up to u t are given, but u t is a purely random process. So, different terms are independently distributed. So, expectation of u t plus 1 given u 1, u 2, u t is same as expectation, the unconditional expectation of u t plus 1, which is 0. And then expectation t u t is equal to u t, because u t is given. So, expectation of u t given u t is u t. So, expectation t y t plus h is equal to mu plus expectation t u t plus h minus theta expectation t u t plus h minus 1. Again, we proceed recursively for h equal to 1. You have y hat t 1 equal to mu plus expectation t u t plus 1 minus theta expectation t u t. Now, this term is equal to 0, and this expectation is equal to u t. So, y hat t 1 is equal to mu minus theta u t, and for h greater than or equal to 2, y hat t h is equal to mu. For example, if you take h equal to 2, then y hat t 2 is equal to mu plus expectation t u t plus 2 minus theta expectation t u t plus 1. Again, remember that u t is a purely random process. So, expectation t u t plus 2 is 0, expectation t u t plus 1 is 0. So, this is equal to mu. Similarly, you can show that for all h greater than or equal to 2, y hat t h is equal to mu. So, for MA1 process, one step ahead forecast is different from the mean, but after that the forecasted value becomes constant. It is equal to mu, the mean of the process. And what is the reason behind it? For MA1 process, you remember that autocorrelation function rho k is equal to 0 for all k greater than or equal to 2. So, any two terms of the time series which have lag more than 2 or greater than or equal to 2 are uncorrelated. Say y t and y t plus 2. So, y t does not have any information about y t plus 2. y t and y t plus 2 are uncorrelated. So, observations up to time t do not provide any information about y t plus h for h greater than or equal to 2. That is why y hat t h is simply the process mean mu for h greater than or equal to 2. The past observations have, or the past information has no effect on the forecasted value or predicted value y hat t h. Then h step ahead prediction errors and their variances are: for h equal to 1, f t 1 is equal to u t plus 1. You can easily verify it. Say here in place of t you take t plus 1. So, y t plus 1 is equal to mu plus u t plus 1 minus theta u t, and y hat t 1 is equal to mu minus theta u t plus 1, and then you take the difference between two. So, you obtain u t plus 1, this quantity. Variance of f t 1 is equal to sigma square u, and for h greater than or equal to 2, f t h is equal to u t plus h minus theta 1 u t plus h minus 1. And then for h greater than or equal to 2, variance of f t h is equal to sigma square u 1 plus theta square, which is same as the variance of y t. Now, for obtaining one step ahead forecast, the unobservable error u must be expressed in terms of observable variable y, because in MA1 process you have expressed the forecasted value in terms of u t or u t plus 1, but this u's are unobservable errors. So, you must express these unobservable errors in terms of the observable variable y. Now, for s less than or equal to t, using this equation 14 and this equation 16, we obtain y s minus y hat s minus 1 is equal to mu plus u s minus theta u s minus 1. From here you get minus mu minus theta u s minus 1 from here, which is equal to u s. So, you replace u s by y s minus y hat s minus 1. So, for t equal to 0, y hat 0 1 is equal to mu minus theta u 0. For t equal to 1, you have y hat 1 1 equal to mu minus theta u 1. Then we replace u 1 by y 1 minus y hat 0 1. So, you get mu minus theta y 1 minus y hat 0 1, and then y hat 0 1 is equal to mu minus theta u naught. So, you get equal to mu 1 plus theta minus theta y 1 minus theta u naught. For t equal to 2, you obtain y hat 2 1 equal to, similarly you proceed like this, then you obtain mu plus 1 mu into 1 plus theta square minus theta y 2 minus theta square y 1 minus theta cube u naught. And so on. In general, y hat t 1 is equal to, you have information up to time t and you are considering one step ahead forecast. Now, for MA1 process, there is no point in considering more than one step ahead forecast, because you know that y hat t h for h greater than or equal to 2 is simply mu. So, we are just taking one step ahead forecast. So, this is equal to mu into 1 plus theta plus so on plus theta to the power t minus theta y t minus theta square y t minus 1 and so on theta to the power t y 1 minus theta to the power t plus 1 u naught. Then mod of theta is less than 1. So, finally, as t increases, the impact of u naught disappears, because since mod of theta is less than 1. So, theta to the power t plus 1 tends to 0 as t tends to infinity. So, the impact of initial other term u naught finally disappears. So, this is how we have developed the forecast for MA1 process for invertible MA1 process. Similarly, we can develop forecast for invertible MAQ processes also. Now, we consider forecast for ARMA 11 process. Again, we assume that the process is stationary as well as invertible. So, this is the process y t equal to delta plus phi y t minus 1 plus u t minus theta u t minus 1, and since the process is both stationary and invertible, mod of phi is less than 1 and mod of theta is also less than 1. Then one step ahead forecast is y hat t 1 is equal to expectation t y t plus 1. And then we take expectation, of course, you replace t by t plus 1 here. So, you get delta plus phi and expectation of y t given the information set up to time t is obviously equal to y t minus, of course, expectation of u t plus 1 is equal to 0. So, expectation of u t plus 1 is 0, you get minus theta expectation of u t given the information up to time t is equal to u t itself. So, y hat naught 1 is equal to delta plus phi y naught minus theta u naught. Y hat 1 1 is equal to delta plus phi y 1 minus theta u 1. Then you replace u 1 by y 1 minus y hat naught 1, because you know that y 1 minus y hat naught 1 is equal to u 1. So, you get delta 1 plus theta, actually you substitute the value of y hat naught 1 from here, and then you obtain delta into 1 plus theta plus phi minus theta y 1 from here plus phi theta y naught, this value minus theta square u naught. Similarly, we can obtain y hat t, say y hat 1 1 you have obtained, then you can obtain y hat 2 1, y hat 3 1 and so on. And then in general y hat t 1 is equal to delta 1 plus theta plus 1 plus theta to the power t plus phi minus theta y t plus theta phi minus theta y t minus 1 plus theta to the power t minus 1 phi minus theta y 1 plus phi theta to the power t y naught minus theta to the power t plus 1 u naught. Just you keep on substituting the values recursively means you obtain y hat t y hat 1 1 from here, y hat 2 1, then y hat 3 1 you obtain, and so on. So, by recursive substitution you ultimately reach here, and then this is a geometric series. The sum of this geometric series is this 1 minus theta to the power t plus 1 upon 1 minus theta, and then you have rest of the terms. Then again as t increases, y hat t 1 is independent of initial value y naught and u naught. These terms will tend to 0. Then for h step ahead forecast, when you take h equal to 2, 3, so on, say y hat t 2 is equal to you have to obtain expectation t y t plus 2, and y t plus 2 you write from the equation of the MA1 process delta plus phi y t plus 1 plus u t plus 2 minus theta u t plus 1. And then you take expectation. So, you get delta plus phi, and this expectation is equal to y hat t 1, expectation of this term is 0, expectation of this term is 0. So, you get this term. So, now it has started behaving just like an AR1 process. Now, y hat t 3 is equal to delta plus phi y hat t 2 and so on, and at last y hat t h is equal to delta plus phi y hat t h minus 1. So, for h greater than or equal to 2, your forecasted values are just like the forecasted values of AR1 process, and the reason is that the effect of MA term vanishes, because MA term is of order 1. So, the effect of MA term vanishes for h greater than or equal to 2, is it has no effect for h greater than or equal to 2. Now, we consider Durbin-Levinson algorithm for obtaining the forecasted values recursively for an ARMA PQ process. So, for ARMA PQ process, it is difficult to obtain the prediction equation. So, we use Durbin-Levinson algorithm to obtain solution recursively. So, initially we take phi naught naught equal to 1 and V 1 naught equal to gamma naught, and then for n greater than or equal to 1, phi n n is equal to rho n minus summation k equal to 1 to n minus 1 phi n minus 1 k rho n minus k divided by summation k equal to 1 to n minus 1 phi n minus 1 k rho k. So, you are calculating these coefficients phi n n recursively, and for n greater than or equal to 2, phi n k is equal to phi n minus 1 k minus phi n n phi n minus 1 n minus k. So, again once you obtain phi n minus 1 k and phi n n and phi n minus 1 n minus k, then you can obtain phi n k. And for n greater than or equal to 1, V n plus 1 n is equal to V n n minus 1 into 1 minus phi n n square. So, this is how you can compute different phi's and these V's recursively. Actually, we have already used this Darwin-Levinson algorithm for obtaining the PACF. There also we used the same algorithm. So, using Darwin-Levinson algorithm, you can obtain the partial autocorrelation function recursively. Same algorithm we are using here also. So, for n equal to 1, you have phi 1 1 equal to rho 1. So, y hat 1 1 is equal to rho 1 y 1. In general, y hat n plus 1 1 is equal to rho 1 y n. Its mean squared error is V 2 1 is equal to gamma naught 1 minus phi 1 1 square. We just take n equal to 1 n equal to 1 and phi 1 1 equal to rho 1. Then for n equal to 2, phi 2 2 you can obtain using the values obtained in this first step, rho 2 minus phi 1 1 rho 1 upon 1 minus phi 1 1 rho 1, and then phi 1 1 is equal to rho 1. So, this is equal to rho 2 minus rho 1 square upon 1 minus rho 1 square. Then phi 2 1 is equal to phi 1 1 minus phi 2 2 phi 1 1, which is equal to rho 1 into 1 minus phi 1 1. And then y hat n plus 1 2 is equal to phi 2 1 y n plus phi 2 2 y n minus 1, and the mean squared error of this is y hat n plus 1 2 is V 3 2 is equal to gamma naught 1 minus phi 1 square 1 minus phi 2 2 square, and then you can substitute the values of phi 1 1 and phi 2 2 here. So, you get the value of MSE, and then we continue these steps for n equal to 3, 4 and so on. So, recursively you can obtain different predicted values, their MSCs, etc. Now, we apply this Darwin-Levinson algorithm for AR2 process. For AR2 process, initially phi 1 1 is equal to rho 1 and rho 1 is equal to phi 1 upon 1 minus phi 2. Phi 2 2 is equal to rho 2 minus rho 1 square upon 1 minus rho 1 square, and you know that this quantity is equal to phi 2. Phi 2 1 is equal to rho 1 1 minus phi 2 2, and phi 2 2 is equal to phi 2. So, rho 1 into 1 minus phi 2 2 or rho 1 into 1 minus phi 2 is equal to phi 1 from here. Then phi 3 3 is equal to rho 3 minus phi 1 rho 2 minus phi 2 rho 1 divided by 1 minus phi 1 rho 1 minus phi 2 rho 2. Then from Yule-Walker equations you have rho 3 equal to phi 1 rho 2 plus phi 2 rho 1. So, this quantity is equal to 0. So, phi 3 3 is equal to 0. Then phi 3 1 is equal to phi 2 1 phi 3 3 minus phi 3 2, and this quantity is equal to 0. So, this is equal to phi 2 1 and phi 2 1 is equal to phi 1. Then phi 32 is equal to phi 22 minus phi 33, phi 21, again this term is 0. So, you have phi 22 and phi 22 is equal to phi 2. Then phi 44 is equal to 0 and so on. So, one step ahead predictor is based on two preceding values. Y head n plus 1 2 is equal to phi 1 y n plus phi 2 y n minus 1. So, this is how you can apply Levinson algorithm for AR2 process. Computing the likelihood function, we use innovation algorithm. In fact, you have not only to obtain the best linear unbiased predictor, but you have to estimate the parameters also for ARMA PQ process to obtain feasible linear predictors. So, we use innovation algorithm for this purpose. So, suppose P t y t plus h is the best linear predictor for y t plus h in terms of y 1, y 2, y t. Then we define one step ahead predictor y equal t plus 1 equal to say 0 if t is equal to 0 and P t y t plus 1 if t is equal to 1, 2, so on. And its MSE is denoted by V t is equal to expectation of y t plus 1 minus P t y t plus 1 whole square. Then the innovation representation of one step predictors is y equal t plus 1 is equal to, we take it is equal to 0 if t is equal to 0, then this is equal to L equal to 1 to t theta t L y t plus 1 minus L minus y equal t plus 1 minus L for t equal to 1 to m minus 1, where m is the maximum of p and q. P and q means we are taking ARMA PQ process. Then this is equal to phi 1 y n plus so on plus phi p y n plus 1 minus p plus summation L equal to 1 to t theta t L y t plus 1 minus L minus y equal t plus 1 minus L for t greater than m. So, you can compute it recursively. And suppose W t is equal to sigma u inverse y t for t equal to 1 to m, and this is W t is equal to sigma u inverse phi b u t for t greater than m, where again m is maximum of p and q. Then the coefficients theta t L and the MSE of predictors can be computed recursively using the innovations algorithm, which is described here. We define the function k I j as k I j equal to expectation of W I W j, which is given by sigma u is minus 2 gamma I minus j if I j lie between 1 and m, and then this is equal to sigma u minus 2 gamma I minus j minus summation r equal to 1 to p phi r gamma r minus mod I minus j when minimum of I j is less than or equal to m, less than maximum I j, less than or equal to 2 m, and then this is equal to sigma u minus 2 summation r equal to 0 to q theta r plus mod I minus j if minimum I j is greater than m and 0 otherwise. And then after suppose R k is the sample ACF, then innovation algorithm is, say initially you take R naught equal to k 1 1, in step 2 you take theta I minus k equal to R k inverse k I plus 1 k plus 1 minus this summation, where k lies between 0 and I minus 1, and for I lying between 1 to m and k between I minus q to I minus 1 for I greater than or equal to m. Further, theta j L is equal to 0 for all j if L is equal to Q. In step 3, you compute Ri is equal to k I plus 1 minus summation L equal to 0 to I minus 1 theta I minus L square R L. So, V j is equal to sigma square U R j. Then under the assumption of normality, you can compute the likelihood function using this expression. And here these are not R1, so on Rn minus 1 are the sample autocorrelations. Then we maximize the likelihood function with respect to phi and theta, which is equivalent to maximizing the log likelihood function. So, we maximize this function with respect to phi and theta to obtain the maximum likelihood estimators of phi and theta. So, we can summarize the maximum likelihood estimation procedure like this. So, in step 1, we initialize the parameters using the Yule-Walker equations, and then we compute L phi theta using innovation algorithm. We compute k I j. In next step, application of one iteration of numerical optimization program will yield new values of phi and theta. Then again we obtain new value of sigma square u, and then we repeat these steps until the changes in the log likelihood function are smaller than some desired accuracy, say epsilon. So, this is how you can obtain the maximum likelihood estimator. So, we have discussed how we can obtain forecasted values, say H step ahead forecast for the stationary and invertible ARMA processes. We have, in particular, we have applied this procedure to AR1 or AR2 process and then AMA processes also. We have also discussed Darwin-Levinson algorithm and innovation algorithm for obtaining the predictors and maximum likelihood predictors as well as maximum likelihood estimators of the parameters. So, here I am going to stop. Thank you.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. I'm here to tell you a little bit about how we can think about globalization in a sociological manner. Now, one of the important concepts in the field of globalization and particularly global studies is that of global flows. It's a term that was developed by the sociologist and anthropologist Arjun Appadurai. He said that as the world is becoming a more and more global place, you increasingly see the movement of different types of things, both tangible and non-tangible, across multiple national borders. To begin with, you can look at how your day proceeds. I often need a cup of tea to actually start my day. Now, if you think about it, tea that we drink is not something that is that originated in India. It's actually a drink that comes to us from quite far away in China. And this is something that has happened not immediately, but it has happened 400 or 500 years ago. So this kind of movement actually happened with the movement of people. Now, this kind of movement of people and goods is one category of flows that Appadurai talks about. A second category of flows could be financial flows. And a good way to think about this is the kind of volatility that you can see in economic markets today. For instance, in 2008, the whole world experienced a very serious economic jolt. Developments in the country of Iceland had a huge repercussion across many, many countries in the world. Now, that gives you an indication of the kind of financial flows that are a part of globalization. So, we are not only talking about money flowing from place to place, but also financial decisions made in one place having an impact on other parts of the world. Appadurai also argues that there is a third category of flows which he refers to as the flow of images or media. Now, this is something that I'm sure you're quite used to. Much of the programming that you watch on television today, for instance, you may actually be watching channels that have originated or programming that's originated elsewhere. More than that, it could also be that the programming that you see today is influenced by shows that have originated abroad. Similarly, you can have content that was made in India, which makes its way to other places in the world. For instance, we know that Bollywood films are extremely popular in many countries across Africa. So this kind of movement of media is, Appadurai considers it to be an important part of globalization. The fourth category that he talks about is the movement of ideas. So this means that ideas that are popular in one part of the world are not restricted to that part alone, but they actually travel across borders. So for instance, something that you may read about in the papers would be, say, events such as gay pride events. Now, gay pride events have their origin in places like New York. But the idea that there should be equality between people, irrespective of what their sexual preference is, that is an idea that has now become popular across the world. And so that's the fourth category of flows that he referred to. The fifth category of flows that Appadurai talks about is that of technology. An easy way to think about this is, let's say tomorrow there is news announced that Apple is going to release iPhone 7. As you can anticipate, there is going to be a lot of excitement in many parts of the world, and people are going to start queuing up, waiting for those products to actually come to their country. So, technology is something that is quite exciting and really moves across various national borders.